In this tutorial, I will show you how to perform energy balances in Excel. To showcase this, I will go through 3 examples in which energy balances were performed using Excel. To begin, we will first look at how we can use Excel to calculate the heat duty required to heat an ammonia stream from 375 Kelvin to 750 Kelvin with a flow rate of 100 moles per minute. To obtain the duty, we first need to calculate the change in specific enthalpy, which we can obtain from equation 1. However, the specific heat capacity depends on temperature. This adds complexity to the calculations. In that case, we require an equation for specific heat capacity expressed as a function of temperature. Such equations can usually be found in literature, including Perry's Handbook for Chemical Engineers, which provides constants A, B, C, and D. These constants are used in a polynomial form to determine the specific heat capacity at a given temperature, as we can see from equation 2. So to begin, let's implement this polynomial into our Excel sheet. Once we have the constants, we can combine equation 1 and 2 to derive the following relationship, which will allow us to calculate sensible heat. This is equal to the change in specific enthalpy at the outlet of the heater. Let's also implement this into our spreadsheet. Once we have calculated that value, we can finally determine the heat duty using the law of conservation of energy. In this specific example, since we are using the inlet condition of the ammonia as our reference point, the inlet energy flow term cancels out. This leaves us with the final equation shown here, which we will now implement into Excel. And with that, we can get our final answer. For the second example, we will perform a heat balance around a condenser to determine the rate of heat removal required. In this case, we have acetone vapor at 100 degrees Celsius entering the condenser at 100 moles per second. At the outlet, the acetone is fully condensed, exiting as a liquid at 25 degrees Celsius. So let's enter the given information for this problem into Excel. Because there is a phase change, we must now account for it in our calculations. Beyond sensible heat, we need to consider the latent heat of condensation. To do this, we need to look at the pathway the acetone takes as it transitions from a vapor to a liquid. From the diagram, we can see that we need to go from the vapor state at 100 degrees Celsius to the liquid state at 25 degrees Celsius. To simplify this, we can take an alternate path that leads to the same end state. First, we calculate the sensible heat required to cool the acetone vapor from 100 degrees Celsius to its bubble point temperature. Next, we can account for the phase change During condensation, the temperature remains constant at the bubble point and the latent heat of vaporization must be included. This value is usually available in literature for various substances. Finally, we can calculate the sensible heat for cooling the liquid acetone from the bubble point temperature down to the target temperature of 25 degrees Celsius. By adding all three contributions together, we can obtain the total change in enthalpy, which we can then implement in Excel as shown. In the third example, we will look at a vaporizer where we have multiple substances, phase changes, and a partially vaporized outlet stream. The feed stream is equimolar, consisting of pentane and hexane, entering at 12 moles per second and 20 degrees Celsius. Both the liquid and vapor exit at 65 degrees Celsius. The outlet information tells us that 40 molar percent of the liquid phase is pentane and that 30% of the pentane in the feed is vaporized. To solve this, we must first perform mass balances to determine the flow rates of pentane and hexane in both liquid and vapor streams. Once we have those values, we can calculate the change in enthalpy for each component and apply the law of conservation of energy to determine the heat duty. Let's start with the mass balances. At the inlet, the feed stream is 12 moles per second and equimolar. So we have 6 moles per second of pentane and 6 moles per second of hexane. There is no vapor at the inlet, so we can enter zeros for these cells. Since we are using inlet conditions as our reference, we don't need to assign values to the enthalpy terms at the inlet. For the outlet, for liquid pentane, since 30% of the pentane vaporizes, 70% remains as liquid. We can use the following equation shown here to calculate the value. For vapor pentane, subtract the liquid amount from the inlet total to find the vapor flow rate. And for the vapor hexane, since the vapor stream contains 40% pentane, we can divide the vapor pentane value by 0.4 to get the total vapor flow rate. Then subtract the pentane amount to find the vapor hexane flow rate. Now let's implement this into Excel. Next, we can calculate the enthalpy changes. For liquid phase components, we use the sensible heat formula, and for the vapor phase components, we must also account for phase changes, following the alternative pathway method we used earlier. Here's the diagram to illustrate. So, to recap, for liquid components, we calculate using sensible heat, and for vapor components, we include phase change enthalpy as well. Let's implement these into our Excel sheet. Finally, we can calculate the rate of heat transfer. Since we are using inlet conditions as the reference, the inlet terms cancel out and we are left with the heat transfer rate shown here, which we can now implement into Excel.